In this video, we're going to look at an example for a finite state machine. We're going to detect a 101 sequence. Our first example is to design a Moore FSM that has a serial input A and output C. The machine must output a C equal to 1 when it detects a sequence of 101 in the input A. Overlapping patterns should be detected too. So we have a serial input A. So we get each of these values in a serial way. And we need to determine the value of C at for each of the inputs. So for example, we first have to understand the problem. So if we determine by ourselves what should the output C be, we can then design our FSM. So first, when we get the first one, the output it's a 0. We haven't got anything else before. So now we have a 0, the output should be a 0. Now we have a 1. And you can see that that's a 101 pattern, right? So our output now should be A equal to a 1. What about now we have a 1, so we get a 0, and then we get a 0. Now this is a 101, so we have a 1. Then we have a 0, a 0, 1, 0, and then we have here another pattern, so that should be a 1, and then we have a 0 and a 1. Okay, so with that in mind, we need to determine what is the behavior of our state diagram first. So we're gonna look at the steps right now. So we need to design the diagram, then the state table, then the state assignment, and the state assigned table. We derive the output logic, then we choose the flip-flops, the flip-flop type basically, and then we can create our flip-flop input table, and then at the end we can derive the input logic. The first step is to create a state diagram. You need to think about what the machine should do. First, we select a starting state. This is a state that the circuit will be entering when first power on or when a reset signal is applied. So think about what should be the initial value for the outputs in that state also. Now, at each of the states, what are the possible input values or the possible combinations, right? If you have more than one input, and what the circuit should do for each of these possibilities. Now you can add new states as you need, and you need to think also what should be the value of the output at each of the states. And all of these questions you have to be considering when you're creating your state diagram. So you need to draw your thoughts. Okay, we're gonna do it now. So we first select the starting state. So we're gonna do a starting state. So that's when we enter and we have a reset, okay? And we're gonna call that state, we're gonna give it a name. That's a state A. And that's our initial one. So what should the value of the output be at this one? It's the first one. We haven't got any other bits before, so at that point, our output should be a 0. Once that we have that, we need to think what are the possible input values or combinations that we can get. So we can get A equal to a 0, right? And we can get A equal to a 1. So those are the values that my input variable can take. In the case of A equal to 0, what's going to happen? It's my pattern starting, for example. No, right? My pattern of the 101 pattern, it starts with what? Starts with a 1, right? So whenever I have a 0, it's like I haven't even started my pattern. It's like I'm going back to my reset, my initial state. So that's the case of a 0, right? What happens when I find a 1. So you start thinking, well, maybe I'm going to start detecting my 101. So you go to another state. So this one we're going to call it B. Okay, and in this case, what is the value of the output? Remember I said that at each state, right, you need to think about the possible input values. Okay, you need to think what the circuit should do and what should be the value of the output at each of the states. So in this case, we have a 0 also. And now we come back to how many inputs can I get. So I can get a equal to 0, and I can get a equals to 1. So imagine at this point, I already detected the first one. So what happens if I detect another one? What would happen? It's like I'm restarting my pattern, right? Think about having these, and these, and these, right? So that's what we're kind of like thinking, looking at. So when we have a 1, 1, it's like I'm restarting the pattern, so I can go back to B. Now, if I get a 0, right? So that means that I have 2 of my bits of my pattern. So now I can go to another state and I can say that's a C. And again, what is the value of the output? In this case, also a 0 because we have not completed our pattern of 1, 0, 1. At each of the states, again, we have to determine what happens if A is equal to 0, what happens if A is equal to 1. So now think about this. I started here, I go there, so I have a 1, and then I have a 0, and what about if I get another, so at this point I have a 1 and a 0. Now, what if I get another 0? So that's a 100, right? That's even like I'm going all the way back to the beginning of my circuit, of my state diagram, sorry. So for that case, we can do, so that's my A equal to 0, and that's my what? A equal to 1. I don't even need this one right here. I can go straight to the beginning, right? So I can go like that. What happens when I get an A equal to 1? So in that case, I already have a 0, I have a 1, a 0, and a 1. So in that case, we call that D, and our output should be 1 now because we already completed. So think about this one. We have a 1, we have a 0, and then we have a 1. Okay? So anything else, it can be returning to a previous state. Okay? So again, at this state, we need to find, what about I find an A equal to 0, or if I find an A equal to 1. So it's going to be interesting because whenever we get to D, we have got 1, 0, 1, right? What if I get a 1 again, which is this arrow? That means that I'm kind of restarting the 1, 0, 1 pattern. So that case will be state B. What about what about if I get a 1, 0, 1, which is all the way to D, and then I get a 0 again? So this kind of looks like I'm in C, right? So I can return this to C. So this is how we go about creating a state diagram. You have to be adding states as needed. You have to be thinking what are the possible input combinations. In this case, we only have A, and it can only take values of 1 and 0. Okay? Now, step 2 is simple. We have to put the information that we have in our state diagram, we have to put it in the format of a table. So we're going to have our current state, and I'm going to change the name So I had said A, B, C, and D, right? So I'm gonna call them now state 0, state 1, state 2, and state 3. And it will become better in a minute why I am changing to the S0, 1, 2, and 3. So we said that when I am in state A, now that is S0, and I get an input of A equal to 0, where does my arrow point in my diagram? So go take a look in the video back or in your notes. You can see that now I'm taken back to state 0. Now if my input is a 1, where do I go? So I go to S1 or state B. So now in the case when I am in state 1, if I get an input of equal to 0, where do I go? So I go to S2. In the case that I get an input A equal to 1, I go to S1. Also, whenever I'm in S2, if I get an input of A equal to 0, where does my arrow point? To S0. In the case of an input of A equal to 1, the arrow points to S3, and so on. So we're just copying the information that we have in the diagram. We're just going to put it into a table. Last case, it's S2 and S1. We also have to fill out this last column for each of the states. So remember that if I'm in a state A, or so I'm going to just could have put an equal sign here. So state A, I had colored in the diagram. So the output was a 0. For state B, the output was a 0. For state C, output is equal to 0. And only in state D, the output is equal to a 1. So now the state assignment. So in order to implement a logic circuit for the finite state machine, each of the states needs to be represented by a specific binary value. We cannot process letters in our logic circuits, correct? So we need to process everything with binary numbers. So what do we mean by state variables? We mean the output of the flip-flop. That is the output Q. Remember, we have a flip-flop, right? We have an input or J or two inputs depending. We have the clock and we have Q, correct? And we also have the Q naught. So this is what we refer to the state variables. So possible values could be 0, 0, 0, 1, 1, 0, and 1, 1. We can also have a 0, 1, which is whenever we have, these are the possible values whenever we have one flip-flop. Whenever we have one variable. In the case that we have two variables, we have all of these combinations. In the case that we have three variables, we can have all of these values, correct? So remember, we have one binary number, we only get these values. Two binary numbers, we can get all these combinations. Actually, this is 3 and this is 2. Okay, so in our case, we have 4 states, so we need 4 possible combinations. Okay, we need 4 different values. For that case, if you look here, we need 2 variables, the Q1 and Q0. That means that we need 2 flip-flops, flip-flop 1 and flip-flop 0. So now our schematic is going to be taking shape, right? So we determined that we need 2 flip-flops. So we have our input logic on the left, we have our output logic to the right, and we also have the flip-flops right in the middle. Okay, so and we said we're going to call it flip-flop 1 and flip-flop 0. And the other thing to notice is that we have not determined what kind of flip-flop. We just know that we need 2 flip-flops. So now we need to give it a different value to each of the states, and that's why I changed the name to S0, S1, S2, and S3. Okay, because what I'm going to do is I'm just going to call it, this is going to be 0, this is going to be 0, 1, is going to be 1 0 and 1 1. Okay, and so for this one is 0 0 0 1 1 0 and 1 1. You can make a note here that this is not the only way to assign the variables. Okay, so this is not the only way. You can say, well, this one I'm just gonna say this is 1 1. This one I'm gonna say 1 0. This one I'm gonna say 0 0, and this one I'm gonna say whatever I have left that I haven't assigned. So it can be assigned in many different ways. Okay, so it makes some sense that if I'm calling this one a 0, I just call it a 0. It will make more sense and easier for us to go through all of the steps. So that's why I usually stick to, whenever I can do like a numbering on the name of the state, I stick to that same number in binary. So that's just the one right here. So now that we have our assignment, the next step is we're going to have our state table. Remember, this is the state table. State table. We're gonna copy again that state table, but now we're going to be using the assigned values that we gave it. So for example, our current state is 0 0 0 1 1 0 and 1 1, and we're just going to recopy our state table. So we said 0 0, so I get a 0 and a 0. I go to a state 1, so put a 0 and a 1, and so that's what I mean by the process being easier if you give it the same name as the number, because now when you say state 1, you know it's a 1 in binary. State 2, you know it's a 2 in binary, and so on. So now we're looking at this one. So state 2. So we're gonna 1 0, state 1 0 1, state 0 0 0, state 3 1 1, and so on. So that's going to be 1 0 and S1. Okay, so that's how we do it. In the case of the output, it remains the same. So the output is fixed to the state. Okay, we don't need it for this step, but we do need it for the next step. So in this, the next step is the derivation of the output logic. So for this step, we can ignore the middle columns of the state assigned table. We can focus in the column that is output and in the column that is current state. Okay, and remember, we're doing what? A Moore machine. So our output is only dependent on this state. So for this step, we can use K-maps, we can use encoders, decoders, whatever becomes easier for the design, or whatever is easier for you. So you can see that in this case, our output C is not that difficult. This is a simple problem. We have that C is equal to Q1 and Q0. Just that, the two Q's ANDed. And like I said, schematic is going to take shape. So now our output logic, and it depends how you want to implement it, it's the C is equal to Q1 and Q0. Next step is to choose the type of flip-flop that we're going to be using in our design. So for the first example, I'm going to choose D because it's the straightforward, simpler version. So for example 1, we're going to go simple way. Remember the behavior of the D flip-flop. I want you to go look at your notes, or you can go look at a previous video that when we covered this, and I want you to look at the behavior of the D. If you remember, the D changes with the Q, the output Q changes following the input value of D. So whenever I clock it, if I have a 0 in the D input, my Q plus, I'm gonna call it, my Q plus is going to be a 0, right? If I have a D equal to 1 at the input of the D flip-flop, my Q is equal to 1. So now you can see that the schematic is taking a little bit more form. Now we determine that we determined if we chose to use the flip-flops. But I also want you to look at this. So we need to be able to design or to read what is going to be the input to the D flip-flop, right? And the input to the D flip-flop is coming from where? From our input logic circuit, correct? So we need to create a table that is going to say, well, if I want my output to be a 0, what do I need to put? What value I need to be put in my input? If I want my value of Q to be a 1, what value do I need to put at the input? Okay, you get that again? Let me repeat. I want a certain value at my Q's. What is the value that I need to be putting in here? So we are not designing this yet. We're just making a table that is gonna say what value do I need to put in here so I get the Q that I want. So we're gonna do that next, and we do that with what is called the flip-flop input table. So we're telling what is the input for the flip-flop that we want. In the case of the D, it's straightforward because we can put the value of Q plus, and what is Q plus? That's the value that we want. That's actually the next state. If you go look at the state tables or the state assigned tables, whenever we say what is the next state, we call it Q plus. What is the next state? So in that case, we're going to put exactly that value that we want. We're going to put into the D column, and you're gonna see in a bit. So this is what I mean. So this is our flip-flop input table. Okay, so we have the current state, we have the next state, and we have the output C also. First of all, we can ignore the output. We can ignore that one. So now, if you look at our state table that we had in a few minutes ago, we have a plus, 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 plus. So these are the Q that I want next, right? What do I need to put in my input on the flip-flop so I get that? In the case of the D, we just said, remember that the flip-flop, whatever you put at the input, it goes to the output. Whatever you put at the input, when you clock it, it goes to the output. So if we want a 0 next, what do I need to put at the input of the D flip-flop? We need to put a 0. If I want a 0 here, what do I need to put in the input of my D flip-flop? Well, I have to put a 0. Again, in the bottom, on the next one row below. If I want a 1 in the output of my D flip-flop, what do I put at the beginning? I put a 1. And so you can see that in the case of the D flip-flop, it's straightforward copying these to here. So I'm just going to copy that. So what values I need to put in the input of the D flip-flop? Whatever I want next. So that's what this means. My D1 columns and my D0 columns, they have to be exactly the same as this one from here. So here you have the final values. Now we need to determine the input logic circuit, okay? So now we have our flip-flop input table, okay? And in this case, you need to think about this as a regular combinational, well, it's actually a combinational circuit. But the format that the table is organized is not very clear. So if you need to think of this as a truth table. What do I mean by that? It's going to have the inputs of A, Q1, and Q0. So these inputs, A, Q1, and Q0, and it's going to have the outputs of D1 and D0. And so let me reformat this table so you can have a better idea. So this is what I mean. So if you go back to your digital systems class, this one you have done many times, right? The one on the right. So this one you have done many times. We have as inputs the A, Q1, and Q0, and we have outputs D1, and you have to find one function for that column. And we have D0, and you have to find a function for that one. Now, I do always recommend that you use your input variables. In this case, we only have one, but whenever you have one or more than one or as many as you want, use them as the most significant bit. It will make this easier to translate from the flip-flop input table to a regular truth table. Okay, so now that you have your truth table, you can use K-maps, you can use multiplexers, you can use encoders to find the combinational logic function. So how do we do this one? So in the case of, we're gonna do D1 as a K-map, and it's a 3 variable, right? So like this. And so we have A, Q1, and Q0. And so we're gonna fill it 0, 0, 0, 1, 1, 1, and 1, 0. And we have a 0 and a 1. So we have 0, 1, 0, 1. So 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, and a 0. And so in this case, we have that one, and that is A0 and Q0. Correct. So remember, we're right here. We have this guy is 0, this guy is 0. So A0, and then we have also this guy right here, which that's going to be A, Q1, and Q0 not. So the final function for D1 is equal to this, A not Q0, or A Q1 Q0 not. What about in the case of D0? Can you figure it out just from the table? It's just equal to A, right? You want to do it as a K-map? You can do this. It's A, Q1, Q0. And we're going to have 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. I'm going to have 0, 0, 0, 0, 1, 1, 1, 1. That is just A. Which is this 4, which is A. Once we have that, we're almost done. The last step is to draw your whole diagram. And remember that we have the clock, okay? And you also have to put the enable here, connect the enable, and the clear, preset clear, and so on. But just in general, you need the clock, you need to be connecting your input logic to the flip-flops, and then the cues connected to the output logic. So that's all I have for this video. I have more examples which are more complex than this one, and you can watch them in a separate video.